Kia ora koutou, no mai, haere mai. Welcome to lesson 28, I believe we're up to, on electric charge. We've already talked about some of the concepts that we're going to cover because we've talked about protons and electrons when we were in the nucleus. We talked about the fact that protons repel each other and the electrons are attracted to the protons. And I may have mentioned, I can't recall, that electrons repel each other because they've got the same charge. So this lesson is going to take those ideas and formalize them a little bit. We're going to talk a bit more about charge in general, what it means to have a charge, how objects get charge, and the forces that result from objects having charges. So our goals are to state the units for charge, state the principle of conservation of charge, describe the methods of charging, apply Coulomb's law to calculate the electric force between two charged particles, and then we're actually going to introduce electric potential energy. We've talked about energies, we've talked about potential energies, and now we're going to look at electric potential energy. And we're going to explain how electric potential energy is stored inside a capacitor. The contents of this lesson are very useful on their own, but they're also critical for understanding the next lesson. The next lesson, we're going to talk about the flow of charges, which is more commonly known as a circuit. So you really need to get to grips with this lesson in order to prepare for the next lesson. First of all, electric charge. We've already talked about it a bit, but we're going to define it a little bit more. We've got the ideas already. Two negatives will repel, a positive and a negative will attract, two positives will repel. So anything that's the same, going to repel, anything that's different, going to attract. Electric charge is a fundamental property of matter, just like mass. An object has some mass, it will also have some electric charge. Remember that we've talked about everything being made out of protons, electrons, and neutrons. Protons have a positive charge, electrons have a negative charge, and neutrons have a neutral charge. They don't have a net charge on them. They do have charge within them. Remember, protons and neutrons are made of even smaller things, so there are charges technically in a neutron, but its net charge is nothing. So we've got everything in the universe having charge properties, and because everything is made out of protons, electrons, and neutrons, how many protons, electrons, and neutrons are in an object determine its overall charge. Does it have the exact same number of protons and electrons? Then it's going to be neutral, right? It's going to have no net charge. Just like when we talked about atoms. For an atom, we talked about an ion being an atom which has not got the right number of electrons to match all the protons. And so charge on a larger scale is exactly the same concept. It's just now we're talking about the number of electrons throughout the whole object, not just on each individual atom. There are two opposing types of electric charge. Just to be really clear, we've already established them, but they are positive and negative charge, such as that of protons and electrons. I say such as because, as I said, with neutrons, it actually comes from things inside them. Not the electron is just negative, but protons do have positive and negative things in them, but we're not going to get into all of that. But a proton, for our purposes, is, as far as we're going to deal with it in this course, a proton is the smallest unit of charge that we will get. Protons and electrons have equal and opposite electric charge. They have positive and negative, but they actually have the exact same magnitude of electric charge as well. You've probably already picked up on this concept of net electric charge, the idea that if something has more protons than electrons, it'll be electrically positive. If it has more electrons than protons, it will be electrically negative. And if it has the same number of protons and electrons, it will be electrically neutral. So a positive ion is positively electric. A negative ion will be negatively electric. So they're the same sort of concept. It's just that for an ion, we're talking about a single specific atom, whereas saying something's positively charged, we're talking generically for any possible object. We don't just talk about atoms. As I've said, we have talked about atoms, we've got ions, we've got that concept, but we talk about net charge on whole objects. For example, a 1 gram sample of copper contains 9.5 times 10 to the 18 copper atoms, 10 to the 18. Every copper atom contains 29 protons. So 9.5 times 10 to the 18 copper atoms contains 2.75 times 10 to the 20 protons. 2.75 times 10 to the 20 protons, but it also would have about that many electrons. If it had exactly the same number of electrons, then it would be electrically neutral. The whole 1 gram sample of copper would be electrically neutral. But if it had a few extra electrons, then it would have a net negative charge. And if it had a few, too few electrons, if it had lost a few, then it would have a net positive charge. As we're going to talk about, you can't gain and lose protons because they're in the nucleus. And if you gain or lose protons, you're gaining or losing a whole atom or changing the element as per your nuclear decay. When we're talking about this kind of charge, we are always talking about gaining and losing electrons, not protons. In order to calculate the forces between charges, we need some way to define charge. In the same way that we can calculate gravitational forces, because we have a way to define mass. We define mass, and then based on the masses of two different objects, we know how much force of attraction there's going to be due to the universal law of gravitation. We need the same analogous idea for charge. We need some way to define charge, and then we can come up with a formula that will tell us the force between two charges based on their charge. So the unit that has been defined for charge is the coulomb. It's written there on the screen, coulomb, and we use the symbol uppercase C, capital C, as our unit for our symbol for the unit coulomb. So whenever we talk about charges, we are always talking in coulombs, but we'll employ those prefixes that we learned way back in the early lessons, the microcoulomb, the millicoulomb, nanocoulomb, and so on. So we do need to remember those prefixes. They will again be used here. Protons and electrons have very specific amounts of charge, very specific, right? This is not a roundabout, this number. This is exactly this number. This is the amount of charge on a single proton, 1.602176634 times 10 to the minus 19 coulombs. That's it, exactly. There's no uncertainty about what comes after that 4. It stops at the 4. Right? If you keep writing the number, it would just be a continuous line of zeros. It stops at that 4. That is the exact charge on a single proton. Every proton in the universe has that exact charge. Every electron in the universe has exactly the negative charge that's the same magnitude. So negative 1.602176634 times 10 to the negative 19 coulombs. Every electron in the universe, full stop. That's it. No ambiguity, no uncertainty. That is the charge. We don't normally use all the significant figures because if the rest of our equation inputs, if we've got masses or we've got numbers of protons or anything, and we don't have that much precision on those values, there's no benefit in using all 10 significant figures in that electric charge. So we normally just use a couple. So you might just get 1.6 times 10 to the negative 19 or 1.602 possibly if you wanted a couple more. We wouldn't normally bother going beyond that, especially not in this course. Since all matter is made up of protons, neutrons, and electrons, any electric charge that any object has, if it's made up out of our standard matter, if it's made up out of protons, electrons, and neutrons, then its total net charge must always be a multiple of the number of protons, or the charge on a single proton or electron, because it's made up of multiple protons. If each proton has exactly 1 proton's worth of charge and you get 5 protons, you've got exactly 5 protons worth of charge. There's no way you could ever get 5.5 protons worth of charge because you can't get half a proton. So we know that the amount of charge on any object is always an exact multiple of that fundamental charge amount on each proton or electron. So the total number of positive charge is going to be equal to the total number of protons in whatever object you're looking at. The total number of negative charge total amount of negative charge is going to be equal to the total number of electrons in whatever object you have. And the difference, if you add them together, that difference is the net charge on an object. So that means that the net amount of charge that an object can have is always a multiple of the charge on a single electron or proton. It always is, because that object will either have exactly the same number of protons and electrons and have a total net charge of 0, or it will have more protons or more electrons, right? It'll have more of one or the other. And in that case, the total number of protons or electrons that it has more than the other is the exact amount of net charge that that object has. So this is an important point because it's reminding us that everything in the universe, whenever we talk about electric charge, everything in the universe, that charge is caused by just an imbalance in the number of protons and electrons. That's it. That's all it comes from. Just as we have conservation of energy, we have conservation of momentum. We sort of had a conservation of mass idea, but we did see that when we form nuclei, some of that mass can be used as energy. So really the conservation of mass is tied up in the conservation of energy. It's just that you can convert mass and energy back and forth. So it's sort of all one thing, but we definitely have conservation of energy, conservation of momentum, and now we have conservation of charge. Charge cannot be created and destroyed, right? The net charge is never going to change. When I say it cannot be created and destroyed, on the scale smaller than protons and neutrons that we're not going to look at, it actually kind of does, but again, we're not really going to look at that, okay? So just to be confusing, it kind of does create and destroy, but it always creates and destroys in exact equal and opposite amounts, right? It'll create one positive thing or one negative thing, that balance, so that the net charge never changes. And in fact, we saw that with neutron decay. Neutrons decay by giving off a beta particle and an electron, and they turn into a proton. So what was neutral now becomes a positive thing and a negative thing. And those charges were already there, they were just inside the neutron, which made the neutron neutral, right? And so when it gave off the electron, it was left with a positive charge and it becomes a proton. But the total amount of charge cannot change. So just like we saw with energy, you can change the charge on any object if you give it some electrons or take some electrons off it, or even give it some protons in certain circumstances, but you can't just create some extra charge out of nothing. So hopefully you've got an idea of what charge is and what we mean by saying an object is charged, right? As a reminder, it just means that there are more or fewer electrons than there are protons in the object. And that is it. That is all we mean by saying an object is charged. Objects by default are neutral. They have matching numbers of protons and electrons, so no net charge, right? So the default status is, just as we saw with atoms, it's that we have a number of protons in the nucleus surrounded by a number of electrons that are the same, and we get this neutral atom, so it's not an ion. And if you go and make a block of copper out of a whole bunch of these neutral non-ion atoms, then that whole block of copper will have exactly the same number of protons and electrons. And that's the default state, right? It's not the natural state. It doesn't mean that's how it's created. Remember that the nuclei are formed in stars in a plasma, like just lots of heat and pressure. So it's not really even what we would recognize as matter when we look at it normally anyway. So it's not necessarily the natural state, but it's what we call the default state, because it's just the neutral, no charge, same number of protons and electrons. So we always refer to that as our default state of matter. But we can cause a charge. We can cause a charge by doing multiple different approaches, right? The first one is friction. If you get two materials that will readily transfer electrons under friction, then you can cause a net charge on both of those objects. Remember that friction was the idea that you have to push parts of one surface, one material out of the way as you move the other material past it. So you might have a bumpy surface, then you've got an object and you're sliding it along and it has to push these bumps out of the way. In some materials, when that occurs, the electrons actually transfer. They move from the bumpy surface to the thing that's pushing the bumps out of the way. If you are seriously interested in it, then it is usually to do with small little bonds forming between the atoms in the surface and the atoms in the object. And when the bonds break, the electrons are more likely to stay on one side than the other, resulting in the transfer of electrons from the surface to the object or vice versa. But that's not necessarily part of this course. Fascinating, I agree, but not part of what we're looking at. We just want to know the net result, which is that if you rub two objects together, then in certain circumstances, those two objects will swap some electrons. They will move from one object to another. If you rub a balloon or a ruler, so certain types of plastic, on your hair, then electrons will be transferred from your hair to the balloon. Your hair becomes positive, the balloon becomes negative. So your hair has lost electrons and the balloon has gained electrons. Your hair has become positive, the balloon has become negative. And as a reminder, your hair has become positive, but it has not gained any protons. If it gained protons, that would mean it has gained whole atoms, and it hasn't gained whole atoms. It has lost some electrons. It has not gained any protons. So your hair is left with a positive charge. The balloon now has a negative charge. And because opposites attract, the balloon and your hair will be attracted to each other. So as you try and pull the balloon away, parts of your hair will stand up, being attracted to that balloon, right? And if you let the balloon go, it would fly back into your head. So they would be attracted because they're now opposite. Positive and negative attract. And this is a good experiment that if you have not done it and you have a couple of balloons and some string, feel free to try it. It is entertaining and it's a very simple experiment. You just get two balloons, you inflate them, and you hang them from the same hook so that when they just hang, they will be touching, they'll bounce into each other. Then you rub them both onto your hair and cause them both to become negative. Your hair will become positive, but we don't really care about your hair at this point. What we care about is the balloons both having the same charge, both being negatively charged. And you then move away and let the balloons go, and the balloons will not fall into each other. They will not touch. They will repel each other slightly. This works because balloons are very light, right? They have very low mass, very low force due to gravity. And so giving them even a small charge is enough to repel them and push them away because you don't need a great force to overcome that weight force. So that's a fun little experiment that you can certainly do at home. And as I've already said 2 or 3 times, and I will keep repeating, the electrons are the thing that are moving. The electrons move. Electrons move because they are relatively easy to remove from atoms. The protons are stuck in the nucleus. The nucleus is the matter, that is the atom, that is the mass. If the nucleus were to move, then the whole atom would be moving and the mass would be moving, not just the charge. So the protons always stay where they are. The electrons move between different atoms and different objects, right? So electrons can move, protons do not move. I don't know how many times I can say this, but I will keep repeating it because it is always one of the points that trips people up. Protons do not move. If a proton is moving, the whole atom is moving, right? Electrons, though, they are relatively free to move. Just as we saw when we were studying thermal physics, some materials, specifically metals, form crystalline solids and share their electrons. So every metal will share its outer shell of electrons. So remember the idea of electron shells. You've got the nucleus and then a couple of electrons in the first shell, a few more in the next one, a few more in the next one, and so on, for however many shells you need to hold all the electrons for that material. When metals form, the outer shell of electrons basically just get shared across the whole metal. So every atom that makes up that block of metal has given its outer shell of electrons to share. So they've got this pool, the sea of electrons that are just shared amongst every atom in that block of metal. So those electrons are free to move. They can move from one end of the block of metal right to the other. They can move anywhere through that piece of metal. Since electrons are negatively charged, these electrons moving about is charge moving about. If an electron moves from one end to the other end, then you've had a negative charge move from one end to the other end of the piece of metal. When the block of metal is on its own, when it's isolated and not touching anything else, those electrons will be moving, but there'll be, if one's moving one way, there'll be another moving the other way, so that it effectively cancels out and you don't have an overall movement of charge. Any material that does this, that has these electrons that are free to move around and carry this charge, they are the charge, and move charge back and forth throughout the material, that is known as a conductor. We talked about the word conductor when we talked about thermal conductors, ones that transport heat well. Now we've got the word conductor for electrical conduction. So it's important to make sure when you're reading a problem or a scenario or thinking about anything in the real world that you are careful about whether you are dealing with a thermal conductor or an electrical conductor. A lot of the time, they will be the same. A lot of the time they will be the same, but there are times when something is a good electrical conductor and not a good thermal conductor and vice versa. Insulators, just as we saw with thermal physics, are the opposite. They are not good charge conductors. The charge cannot flow very well through them. The electrons are generally still stuck on their shell of the atom, so they can't move without getting a heap of energy, right? So generally, the electrons will be pretty much stuck where they are, and so charge cannot move through insulating materials very well. So just as we saw with thermal physics, insulators and conductors just mean good at moving charge versus good at moving thermal energy in the thermal physics section. When we draw diagrams to illustrate charges, which you will be expected to do when you're dealing with a scenario involving charge, we often use little plus and minus signs to represent the charges. They don't need to be a specific amount of charge. They can be if you know the exact amount of charge. Remember the unit for charge is coulombs. So say we had a charge of 3 coulombs, you might draw 3 plus signs, each one representing 1 coulomb. But each plus would only be a symbol representing that amount, is not representing a single proton or anything like that. They are purely to give a visual representation of the net charge because, remember, the charge on these protons and electrons, 1.6 times 10 to the negative 19 coulomb, we would have to draw ludicrous numbers of these pluses and minuses if we were to represent every single proton and electron. Not practicable and also not useful. Doesn't convey any information to us. And the whole point of these diagrams is to convey information. So we want to do that as simple, but as clearly as we can. We want to be very clear and obvious about what is happening, but we don't want to make our diagram so cumbersome that it's impossible to interpret. So what you need to do when you draw such a diagram is make sure that the plus and the minus, regardless of how much they represent, that each one represents the same amount, plus some amount and negative the same amount. And every plus is the same and every negative is the same. So in our diagram here as an example, we've got a conductor with a net charge of 0. But what it's got is it's got negative charges on one side and positive charges on the other. And so we have to draw the same number of negative and positive. Otherwise, the net charge wouldn't be 0. We don't know how much each plus and each minus represents. It doesn't matter. What matters is that each one represents the same amount, different magnitude, different direction, plus and minus, but represents the same magnitude of charge, and by having the same number of each, we have a net 0 charge. The idea of having plus and minus on opposite sides is something we'll talk about soon. Charge distribution. If you have any object that is a conductor, so the electrons are free to move around, right? Well, not all of them, but a bunch of them are free to move around. If it has a net negative charge, those electrons will be repelling each other, right? The electrons in the object that match all the protons. Remember though, if you have an atom and a metal atom that's forming an object, and it's got a certain number of protons, and it joins this block of metal, and it gives off its couple of electrons, and maybe it's got 2 in its outer shell, and it gives them up to the sea of electrons. That atom is now a positive ion. It's now got positive 2 charge if it gave off 2 electrons. So that positive atom will generally have a couple of electrons hanging around it in the sea of electrons. There'll often be a couple to sort of balance it, and that'll be true for every electron. So that each atom will still need a couple of electrons in the sea to balance it. And what we're saying here is that on top of that, we've got some more electrons. So these are extra electrons that don't actually balance any of the atoms in the metal object, in the substance. So we've got these extra electrons. What are they going to do? Right? They're not attracted to the positive ions because those are already sort of balanced by having a couple of electrons in the sea. So we've got these extra electrons, and these extra electrons are all negative, so they are actually going to repel each other. And what they're going to want to do is get as far away from each other as possible. And the way that they do that is to get to the surface of the conductor. They get right to the outer edges of the surface, and they spread out evenly across the surface. And this is exactly what happens, right? And that's why it happens. It's that simple. The electrons repel each other. The furthest they can get on a conductor is right to the surface, as far away from each other as they can. As soon as they go inwards, they're moving closer to some of the other negative charges. So they're not going to do that. They're going to go as far away as they can, which is always on the surface. So on a conductor that has a net charge, it is always distributed across the surface, right? Full stop, that end, always on the surface. Whenever we draw them, then we try and indicate that by drawing our charges near the edges of the object. So the top diagram there is correct. All the extra electrons repel each other, so they're all spread out around the edge. Obviously, I can't draw them the size of the electrons or literally on the edge, or it would just get messy, but I draw them just inside, but near the edge, to indicate that they are spread out at the edges of the conductor. The bottom diagram is incorrect. It still has the same number of negative charges, so it is correct in the idea of the net charge being the same as the one above it, but it doesn't represent that distribution that we know occurs. So we want to include that idea of this distribution, this uniform distribution. Likewise, you could go and draw all eight charges. Is it 8 here? I think it's 8 charges on one side of the conductor at the surface, and you might think, oh god, they're all on the surface, but they're still closer together than they need to be. And so they would spread out uniformly across the whole surface. So that top diagram really is the correct way to draw it. Positive distribution, exactly the same. They distribute themselves across the outer edge of the material. But please remember that these are not protons in the sense of a proton's moved itself to the surface of the material. They are unmatched protons. So the protons are still in the nucleus. So each plus here is actually representative of atoms which don't have matching electrons in the C. Remember, I was talking about each atom gives off a couple of electrons. Now it's left 2 positive, right, with positive 2 charge, but it will sort of attract a couple of electrons from the C. It's just that those C ones are free to move around, and they could jump to that one if one jumps back and so on. So they're free to move around throughout the material. But if you don't have enough electrons, if you take a bunch of electrons out of that electron C, now there are going to be a few atoms which cannot have a couple of C electrons hovering around it. And those atoms will always end up being the ones on the surface for the same reason, right? For the same reason, the electrons will go inwards a little bit and leave the surface as a slightly positive charge, rather than putting the electrons all around the surface and leaving a negative charge, a positive charge in the middle. So you don't need to worry specifically about all of that interior detail, the idea of the sea of electrons matching the ions and spreading itself out necessarily, but you do need to remember that regardless of positive or negative charge, it will distribute itself across the surface. If it's electrons, then the electrons themselves have traveled to the surface and spread out across the surface. If it is a positive charge, then it is because the electrons have gone inwards and the outer surface is full of atoms which have unmatched protons, right? So the protons haven't moved, it's just the electrons in the C have moved away from the surface slightly. If we've got 2 conductors, so conductors allow electrons to flow, and you bring them into contact, then the electrons will do just that. They will spread out. Remember that they always want to spread themselves out as far away from each other as they can across the surface of the conductor. And if you bring 2 conductors into contact, they now behave like one conductor because the electrons can move freely through that connection, through that surface touch. Electrons can move from one to the other. So if you do that, if you have 2 objects, as per the diagram here, one with a negative 2 coulomb charge, one with a 0 coulomb charge, so it's still full of electrons, remember, it's just neutral, it's got the same number of electrons and protons, bring them into contact, those electrons, because there are more of them on the negatively charged object, will flow, some of them will flow through to the other object, and they will spread themselves out evenly. If these 2 conductors are identical, then the charge spreading out perfectly evenly across both will mean that each of those 2 spheres ends up with exactly 1 coulomb of negative charge. And then if you pull those 2 spheres apart, they now each have negative 1 coulomb. And that's just a result of the charge distribution. So charging by contact, allowing electrons to flow from one conductor into another, is just a result of that charge distribution, the electrons repelling each other and wanting to spread out as far as possible across the surface of the conductor. So that's all it is. So that will split evenly with half and half. To reiterate, if an object allows this flow of electrons easily, we call it a conductor. If it does not, we call it an insulator. Right? So conductor and insulator, remember those terms, because we're now going to talk about induction. Right? Induction, opposite charges attract. So that means that we can actually cause a net charge, sorry, not a net charge, we can cause a charge distribution, which is not our default distribution of all of the electrons being on the surface, or all of the electrons being slightly in and leaving a positive charge on the surface. Right? We can cause a charge distribution that is not one of those. And the way we can do that is the same as what we were just talking about with 2 conductors, but this time we don't actually let them touch each other. We bring that to negative 2 coulomb charged ball and we bring it really close to our neutral one, but we don't let it touch the neutral one. What that is going to do, because that negative 2 coulomb ball is negatively charged, it is going to repel electrons within that neutral sphere. And those repelled electrons will travel to the far side. They'll try and get as far away from that negatively charged sphere as they can. So what happens is that a few of the electrons that are balancing around some of these positive ions in the metal nearest the negative sphere, they will leave, and they will leave some unmatched positive ions. So you now get a positive side to your sphere closest to the negative charged object. And on the other side of that neutral sphere, where the electrons run to, you now get a net negative charge if you just look at that side of the sphere. So what you end up with is the sphere which does not have a uniform charge distribution. It's got a positive side and a negative side. and that is as per that diagram there. So you can certainly cause non-uniform charge distributions by having other charges nearby. This process is known as induction, right? You induce a charge on a charge distribution on a neutral sphere by bringing another charge nearby, or it doesn't have to be a sphere, it can be any object. You can actually use induction to cause a charge on an object. Remember that if you touch two objects together, two conducting objects together, they will behave sort of like one because electrons can flow freely from one to the other. So what you can do is you can take two neutral conducting spheres, A and B in this diagram, put them into contact so they're touching, and then bring a negative thing nearby. Don't touch it to it, just bring it nearby to one of the spheres, and that will cause that charge induction. It will cause a non-uniform charge distribution because it will basically push some of the electrons away. So some of the electrons from A will get pushed into B. And if you separate A and B while that negative charged object is still nearby, you separate A and B, those electrons now have no way to get back from B to A. If you then take away the negative object, A and B will end up with uniform charge distributions, but they will no longer be neutral. Now A will be slightly positive and B will be slightly negative because some of the electrons from A got pushed onto B while they were touching when that negative charge was brought nearby and causing a charge induction. So you can use induction to create a charge on two different objects by causing the electrons to move from one object to the other. Polarization is a term that chemists or anyone studying other sciences may be familiar with. We haven't really used it yet. So far, we've talked about the idea that you've got an atom, it's got a positive charge in the nucleus, negative charge outside it, and they balance. But sometimes the electrons will spend more time on one side of their shell than on the other. And what that means is that that side of the atom will be a bit more negative and the other side will be a bit more positive, because the protons aren't balanced as well, because the electrons aren't spending as much time over there. And that's called polarization. So the polarization is the idea that one side of your atom might be a bit more negative than the other side because the electrons are spending a bit more time on that negative side for some reason. And there are a variety of different reasons. One of them is the chemistry involved in forming some molecules, and water is the classic example. And in water, hydrogen shares its electron. Hydrogen has a single electron, remember, but it shares that electron with oxygen. So here's your hydrogen, here's your oxygen. The electron gets shared by hydrogen to oxygen, but the electron will spend a lot more time, right? A lot more time around the oxygen. So the hydrogen gets a bit less of that electron. A bit less of the electron's time is spent around the hydrogen. The hydrogen, being a single proton, is therefore got an average of less than one electron because the electron is spending some more time at the oxygen. And so that leaves the hydrogen being net positive, right? Net positive charge on the hydrogen. And remember, there are two hydrogens, one oxygen. So the two hydrogens are both positive, the oxygen is negative, and our molecule as a whole has this charge polarization, right? It's not because there is an actual positive or negative end to the hydrogen or oxygen atoms or anything like that. It is literally just because the electrons that are shared between the hydrogen and oxygen spend a bit more time around the oxygen. So on average, there are more electrons around the oxygen end than there are protons, and on average, there are fewer electrons around the hydrogen end than there are protons. And so it gives us positive and negative end. And that is actually the reason for a lot of the interesting properties of water. We talked about the idea that water gets less dense as it freezes, as it becomes ice. That is purely because of that polarization and the way that that forces the molecules to form into its solid structure. It also allows for water to carry electric currents. That's why it's dangerous to have electric circuits near pools of water and things like that. We're not going to go into any of that right now, but it is an interesting property of water. But that can happen on any molecule, and it can also happen on bigger objects like cells in wood or paper. It can happen in things that are insulators. So if you have an insulator, remember that in an insulator, the electrons are pretty much stuck where they are. They are stuck to the atom. They're not free to move like they are in conductors. But they can spend a bit more time on one side of the atom than the other if there was something influencing them. excuse me, influencing them to do so. And that's pretty easy to cause, such as bringing a negative charge nearby. So this diagram here, we've got a block of wood. The wood is full of insulating atoms, so they do not allow the electrons to travel from one to the other. But if you bring a negative charge nearby, it will just repel all of the electrons on every single atom very slightly. And that means that the electrons will all spend a little bit more time on the far side of the atom away from the negative charge than they would on the close side. And that does exactly what we've been talking about. It leaves all those atoms polarized. So we get a slight positive charge on the side of the wood facing the charged object and a slight negative charge on the other side. That polarization is not permanent. As soon as you pull that negative charge away again, the electrons return to normal and the object becomes unpolarized. But you can induce a temporary polarization in insulators using this effect. There are reasons to do that, but nothing that we're going to get into right now. So electric force, we've talked about charges, we've talked about causing objects to be charged, talked about what a net charge is, and it's always a multiple of protons or electrons charges, so on and so forth. What about the forces that result? We know that two objects will repel or attract based on their charges. So we want to determine how strong that force is. There are only a few values in a system of two charges. If you take two objects, you put them out in the vacuum of space with nothing else nearby, so there's nothing in our system that we have to worry about, nothing in our scenario we have to worry about. We just have these two objects with their charges. All that actually matters is the magnitude of each charge, Q1 and Q2. Q is a very common term for charge for some reason, so we're using a lowercase q1 and q2 for our two charges, the distance between them, and the resulting force. That's the only actual values of interest. Yes, the objects will have mass, but that's not going to affect this force. It'll affect the acceleration the object experiences as a result of the force, but it won't affect the force itself. Just the charges, the distance. That's all that matters. As we saw with protons and electrons, charged objects result in both attraction or repulsion. So we can figure out the direction quite easily. But the magnitude of that force will increase if the magnitude of the charge increases, just like gravity. If you have an object that's twice as big, you're now going to get twice as much force due to gravity. And the same thing here. If you double the charge on an object, you're going to double the force that that object experiences in relation to another charge. If you double both of them, it becomes 4 times as big, and so on. The other thing that matters is the distance. So yes, you can change the force by changing the charge on the objects, but you can also change the force by changing the distance between them. If you put two objects really close together, then they will be more strongly attracted than if you pull them further apart. That attraction gets a bit weaker. And that was just like gravity. Remember that in gravity, we had this inverse square law, the inversely proportional relationship that the force had this 1 over d squared or r squared term in it. Same thing here, exactly the same idea. If you move away by twice the distance, your force gets 4 times as weak, right? The inverse square law. So that means we know that the force is proportional to both of the charges, Q1 and Q2, and it's inversely proportional to the square of the distance. So that gives us this relationship. F is proportional to, so that little squiggle means proportional to Q1, Q2 over d squared. So proportional means that we don't yet know the exact relationship and we need some kind of constant in our formula. Those are the only 3 things that we can change in order to affect the force. But in order to get a force in newtons from these charges in coulombs and a distance in meters, we need some other term in there to make the calculation work. But the important thing is all in this relationship right here, the 2 charges and the inverse square. The constant is known as proportionality constant, very imaginative. This is Coulomb's law. Coulomb's law is when we bring in that proportionality constant. And the value of K is 9 times 10 to the positive 9, so a big value, 9 times 10 to the 9 billion Newton meters squared per Coulomb squared. And that gives us our equation of the force due to the charges on 2 particles separated by a distance d is equal to K times Q1 times Q2 divided by d squared. I do recommend that even though you're probably happy to take my word for it, you go through and you check the units work. We have a force on the left, we have K with the units just given right there on the right. We also have on the right 2 charges and a squared distance. So worth your time to just double check all those units work. As I mentioned, we already know the direction of the force. Coulomb's law tells us the magnitude, but we need to think about the direction ourselves. Use Coulomb's law to figure out the magnitude, but always go back to the scenario, go back to your little diagram and think about the direction. This was the same thing that we did in mechanics. I would often say, don't stress about positive and negative, trying to remember if everything's positive or negative and then just relying on that. Rely on the formula to give you the magnitude, but rely on your common sense. You're looking at the scenario, drawing a diagram if you need to, and thinking about that in order to figure out the direction of that force. So if you have two oppositely charged objects, the Coulomb's law can tell you the direction, the magnitude, and you know the direction will be directly towards each other. That's what attraction means. They'll go directly towards each other. If you have two objects with the same charge, both positive or both negative, then again, Coulomb's law can tell you the magnitude, but you know that the direction is going to be directly away from each other. They're going to repel. So you draw a straight line through the two objects. The forces will be on that line, either towards or away from the other object. Now that we can calculate the force between two charged particles, there are lots of scenarios where we can bring Newton's laws back into it. So Newton's laws from the first half of the course, from our mechanics section, you can bring all of that back in. If you know the masses and charges of some particles, and you can calculate the electric forces on those particles due to their charges, then you can use F equals ma to determine the acceleration of the particles. So you can bring Newton's laws into a lot of these physics scenarios now where we're dealing with charges, because we have a way to calculate the force. The one thing I would point out is that if you do calculate the force, so you have two objects some distance d away, some charge on each one, and you calculate the magnitude of the force according to Coulomb's law, and you use Newton's second law to figure out the acceleration of each particle, that force is going to change immediately. So it's not a constant acceleration scenario, because as soon as those objects move, whether it's towards each other or away, your distance has changed. And Coulomb's law depends on the distance. So as soon as that distance changes, you now have a change in that force due to the electric charges. And so the acceleration is going to change. So it's not constant acceleration. So we can't go and use our kinematics, but we can use our Newton's laws. The next part is electric potential energy. We've talked about energy a lot throughout our mechanics section, and indeed all of temperature was all energy. So what about energy for this section, for electric charges? If you have two like charges, they want to repel. A positive and a positive, push them together, they are repelling each other. You have to do work to bring those two charges together. You have done work, you have applied energy to the system. And our useful analogy of a spring comes back again. The idea of these two things being repelling, you can imagine it like a spring. If you take these two positive charges and you push them together, it's like compressing a spring. And if you release them, it'll be just like a spring. They'll fly apart again. So it's just like a spring, but instead of elastic potential energy, we call it electric potential energy. So this electric potential energy is the idea of the energy being put in to some charges to bring them close together when they want to repel. And if you somehow hold them in place, you hold those electric charges near each other, then there is some electric potential energy there. And if they are then allowed somehow to be released, they will use that energy to push apart and repel each other. So electric potential energy, very similar conceptually to elastic potential energy. The amount of electric potential energy a charge has is dependent on how big that charge is. Remember that if you double the charge, you double the force. So say we've got a single proton here, we take one proton and we push it in really close. We have to do some amount of work on it. But now instead, say we have a helium nucleus, which is two protons, and we want to push that to the same location. Because that charge is twice as big, the force is now twice as big. This charge hasn't changed, so just this one has, which means we've just got twice as much force. So now you've got to put twice as much work in, because no matter where you are, that force is always twice as big, because it is proportional to the product of the charges. So twice as much charge, twice as much force, twice as much work means twice as much electric potential energy once you get it to the same spot. So a single proton had some amount of electric potential energy in some location. A double proton, a helium nucleus, for example, would have twice as much electric potential energy. Right? So the the same is true for any charge. If you take some amount of charge and it's got some amount of electric potential energy at some location, and that electric potential energy at a location is always because of the surrounding charges, right? There'll be other charges in the environment that it was repelled to or possibly attracted to, and you've had to pull it away. Regardless, it got to that position somehow, but it had to have some work done on it, and that means it's got electric potential energy. If you replace that charge with one of twice as much charge, that object with one is twice as much charge, then it would have twice as much electric potential energy. Hopefully you can all agree. Hopefully that makes sense, right? If you double the charge, you're doubling the force. Doubling the force means that as you push the object into its position, you're doubling the work needed. So therefore you're doubling the electric potential energy. Since a charge twice as big in the same location has twice the electric potential energy, then that means the ratio, the electric potential energy per unit charge, is exactly the same. Remember our idea of one proton and one proton, you push it in, it's got some amount of electric potential energy. Two protons, you push it to the same location, it's now got twice as much energy, but it's also got twice as many protons. So it has the same amount of energy per proton in that same position as the single proton did. Right? And that ratio is very important, it's very useful, and it is called just electric potential, no energy term on the end there. I personally not a big fan of that naming convention, electric potential energy being the work done essentially to get that object there, the electric potential energy, and then electric potential being electric potential energy per unit charge. I find it a bit of an odd term to call it electric potential. The other name for that term though, for electric potential, is voltage. Voltage, when we use the capital V for volts. The unit is volts, the unit and the term voltage both use capital V, but voltage and volts are both the term and the unit, the quantity and the unit for that quantity. You do need, unfortunately, to remember the term electric potential. You do need to be able to distinguish between electric potential energy and electric potential, which is also known as voltage. Both are very common, so you need to be able to use both. Electric potential and voltage mean the same thing. Electric potential energy is the energy overall for the object. Electric potential or voltage is the electric potential energy per unit charge in the object. A potential of 1 volt is an electric potential energy of 1 joule per 1 coulomb of charge. Right, so that's all a potential is. So that's where the term voltage comes from, which, as I mentioned, you need to be comfortable with this lesson in order to pick up the next lesson on circuits and flow of charge. And this is probably giving you a bit of a hint as to why you need to be confident in that. You can store electric potential energy. Right? Just like we can store elastic potential energy, if you go and compress a bunch of springs and lock them in place, you've stored a bunch of elastic potential energy. That's quite common in sort of spring-loaded guns. You then can release that energy and fire the object off. Same thing here, you can store electric potential energy by locking some charges in place. And then if you release them somehow, you can release that electric potential energy. Suppose you have two flat conductors, two big sheets of conductor, and you use a device to pull electrons off one conductor. That leaves a net positive charge on it, and you put them onto the other conductor, and that leaves a net negative charge on that conductor. That takes work. The very first electron you pull off the initially neutral sheet doesn't take too much work because you're pulling one electron away from a sheet of millions of electrons or billions of electrons. Right, you're pulling one electron out. It's not making a huge difference. Putting one extra electron onto a big sheet, again, not making a huge difference. By the time you've pulled heaps of them off and you've got a really big positive charge on that sheet, each additional electron is really hard to pull off now because you've got an electron has still got the same charge, but that big sheet that you're pulling it away from now has a really big positive charge. So that force is a lot greater. So the work is a lot greater. So the electric potential energy becomes a lot greater. Right, so it becomes harder and harder the more you pull off. But regardless, you pull them off, you are doing work on every single electron, even that very first one, you're doing work on them. You end up with a bunch of positive charge on one plate, a bunch of negative charge on the other plate. And then if you disconnect them so that there's no way for the electrons to flow from the negative one back to the positive one, you now have electric potential energy stored in these two plates, and that is called a capacitor. It's a very, very common item, a common component of circuitry and electronic systems. And that's all it is. It's just the idea of storing this electric potential energy. And as I've put with a little subscript there, the device that we use to do that is actually just a battery. That's all it is. It's just a battery, but I haven't explained batteries yet. We will explain them in the next lesson, which is why I just called it a device for now. Finally, a Van de Graaff generator is a fun little device. The idea of a Van de Graaff generator is very similar to what we just saw for a capacitor, but what it actually does is it just stores the positive charge on the metal dome at the top, and it throws away the negative charge. It doesn't care about them. So it's not really creating the same device as a capacitor, but it is similar. It's just doing one half of it. So the same way as you rub a balloon or a ruler on your hair and you use plastic to cause this charge to move electrons from one object to another, use friction. The Van de Graaff generator does the same thing. It has an insulating belt made of rubber often or fabric, and it rubs that against a brush and causes it to get a charge, which it then transfers onto the conducting sphere at the top. If a person holds that conducting sphere while being isolated, if you're holding it and you're touching the ground at the same time, then any extra charge that the machine gets, the sphere gets, will just travel through you and back to the ground, and it will become neutral again. So it's not actually useful. But if you are insulated, so you stand on a nice plastic platform or something so no electrons can flow through you, then you and the metal sphere become the positively charged thing. So you become positively charged, and as you become positively charged, that charge wants to spread itself, it wants to distribute itself right throughout as far away as it can across you and the sphere. And the best place on a human for that to occur is actually in the hair, because the hair can all stand on end and get far away from each other. So what happens is that that charge distributes itself in the tips of your hair, and your hair all separates and stands on end like that. So that hair is standing on end purely because it has had a bunch of electrons removed from it, leaving it all with positive charge and therefore repelling each other, and so it stands on end. You'll notice a lot of people have noticed the same thing on trampolines, for example. The more you bounce on it, the more your friction with that insulating surface. The trampoline surface is an insulator. The more you rub on that, the more charge transfers from you to the mat, and the more positively charged you become, and therefore the more your hair will stand on end. So that's the end of this lesson, which covered, as I said, electric charge. As I mentioned at the start, and again as we were discussing electric potential or voltage, please do make sure you're happy with the contents of this lesson before starting the next one on flow of charge. It will make it a lot easier to understand circuits if you are fully confident in the concepts here. Not necessarily the exact formulas, although you do need to be confident with them as well, but the concepts here will make understanding circuits a lot easier.